Okay, so question 1, in the figure below, the wavelength is 1 meter, 8 meter, 2 meter, 4 meter. It cannot be determined. Okay, there's a short answer to this, but let's just go through a little bit of learning because I am a teacher, so you're going to have to deal with it. So I'm going to graph here some harmonic motion, just to label a couple things. The distance from max or minimum displacement to the equilibrium position is called your amplitude. So that could either be there to there or there to there. Assuming I drawn this correctly, then that would be equal distances. So the amplitude is really the y value. So in this case, the amplitude is 4. The wavelength is the distance from either crest to crest, or I drew that opposite. That's trough to trough, or it could be crest to crest. That is called a wavelength, also called lambda is your variable for that. Another way you can view it is the distance from the start of one wave to the start of the next wave. So all these things that I've just done right here, this and this and this, they're all equal, and that is the wavelength. However, notice here that your your x-axis measures only time. So there is actually no way of knowing exactly what the wavelength is. Now, if they told you what kind of a wave is, like if it was an electromagnetic wave or a radio wave or something, you could use v equals f lambda, because you could figure out because you know what the velocity of all radio waves are, or electromagnetic waves, and that's the speed of light. So you could conceivably get lambda that way because you could tell how long it takes for a single wave to oscillate. That's a period. But since they don't tell you that, you don't know what the wavelength is. Again, if they simply told you what kind of wave it is, you could probably figure it out, but they didn't. Okay, so question number 3. A wave with an initial wavelength of 3.4 centimeters and a frequency of 16 hertz travels into a new material where the wavelength is 1.8 centimeters. What's the new speed of the wave? Okay, first things first is v equals f lambda. This is called the wave speed formula. The next thing you got to sort of understand is that when a wave enters a new material, so let's just, I'm just drawing a simple picture here. So let's just say we got a new material here. When a wave enters a new material, it's going to slow down and the wavelength will shorten, but the frequency is going to be the same. So long story short is that the wave will slow down and the wavelength will shorten, but those two things together basically cancel each other out, meaning that the frequency stays the same. So now that we know the new wavelength is 1.8 centimeters, we can figure out the speed of the wave just by using this formula. So v is going to equal 16 times 0.018. And when you crank that out, 16 times 0.018, you get 0.288 meters per second. And that is pretty simply how you do that one. Okay. So here, oops, I gotta erase that. Question number 2. A sound source emits 35 watts of sound power spread equally in all directions. What is the sound intensity in decibels 16 meters from the source? All right, this one took a little bit of research because it has been forever since I've had to deal with sound. We don't really do that at the high school level too much. Anyways, here's what I learned. First things first is let's just use the formula for figuring out decibels, because that's eventually what we want, right? So that's going to be 10 log 10 of the intensity divided by sort of the threshold. This is the threshold of hearing, human hearing. And for humans, that's 1 times 10 to the negative 12 in terms of intensity, which is watts per meter squared. Long story short, that's 10 to the negative 12. Okay. What we want to do is we got to figure out what is the intensity at this spot. And then once we have that, we can calculate. So this is where it took a little bit of looking, and it's because normally what you need is you need 2 points. You need a point here and a point here, and you need a reference point here for how loud is it here, and then you would need a distance from here to here to figure out how loud is it here. Notice that we are not even given that initial thing. So this is where I had to do a little bit of looking. But now that I know the answer, it makes sense. So the key here is how it describes the sound power being distributed. Here is the source of the sound, and it is distributed equally in all directions. So if you think of it this way, it's sort of spreading out like this in all these different directions, but equally, right? And we're trying to figure out, at this point right here, what's the intensity right there, right? Because remember, this whole point, we're trying to figure out this intensity value right there. So, turns out that intensity is equal to power divided by area. The power is 35 watts. Now the area that is distributed across is the area of the circle, which is pi r squared, which is pi. Now the r value is 16. So when you do that, you get 35 divided by parentheses 16 squared times pi. Oopsies. So 35 divided by pi times 16 squared. I'll just do it that way. What the heck? Okay, hold on one second. 35 divided by pi times 16 squared. Something's wrong with my calculator. There, now we finally got it. It is 0.04352. I'm rounding it now. Okay. So now we can do this. We can go, the loudness is going to be 10 log of 0.04352 divided by the threshold of hearing, which is 1 times negative 12th. And when you do that, you're going to go 0.04352 divided by 1 times 10 to the negative 12th. You're going to get a really big number for that. Then you're going to take the log of that value, multiply it by 10, and you end up with about 106.8. I believe it was 0.8 decibels. We'll round it up to 107. Again, it was 106 something, but I had to clear my calculator. But I believe it was around 107 decibels.